This video has to do with finding inverses to functions. A function has to be one-to-one in order for its inverse to also be a function, but we're going to talk about that if we haven't already in class, what it means to be one-to-one. I'm just going to focus on assuming that if this function is one-to-one, then we can find its inverse function. Real briefly though, a one-to-one function is a function that not only for every x there is only one y value. In other words, it passes the vertical line test here. There's not an x value that has more than one y value. It has to also pass a horizontal line test that for every y value there's only one x value. It doesn't cross more than once this way either. And let's just go ahead and find this function's inverse, well, from a graph. So what we have, I already recorded them. I just took some points off the graph. 1, 4. All right, input of 1, f of x would be 4 when x is 1. 0, 2, negative 2, 1, and negative 4, negative 2, and I just put them here in a chart. Well, what I'm going to do is I'm going to go ahead and just really reverse those. That's really what an inverse function is where what was an input to the original function becomes the output to the inverse. And what was the output to the original function becomes the input to the inverse. And so what I'll have right next door here is the inverse function, and the notation is that is f minus 1 of x. That is the inverse function to f of x. Well, so I'm going to take 4, 2, 1, and negative 2. And because they were the outputs to the function, they'll be the inputs to the inverse. And I'm going to go ahead and take 1, 0, negative 2, and negative 4 and make them the outputs to the inverse function. And now I could actually plot the inverse function. And let's go ahead and do that. So at 4, 1, I'd be here at 4 and 1. 2, 0 would be at 2, 0 here. 1, negative 2 would be 1, negative 2. And negative 2, negative 4 would be at negative 2 and negative 4. And what you're going to see when I connect these is you're going to see a reflection about the line. This is the imaginary line y equals x. And it's because they're flip-flopped. What was x here is y here, and what was y there is x here. Right? And any time you would graph a function and its inverse, both on the same graph, you will have a reflection about the line y is equal to x. Okay, so let's go ahead and do this. Let's see if we can actually develop our own inverse function from an algebraic view, not just from a graph view. And when we do that, we're going to also go ahead and prove that they're inverses by using a composite, which I'll demonstrate here in a minute. So here's the first question. Let's find the inverse to the function f of x is equal to 3x plus 6. And as I just demonstrated on this graph form of this idea, that we turn things around. What was x now became y, and what was y became x. So we're going to algebraically do that to this problem. If we said this is basically y is equal to 3x plus 6, to find the inverse function, I'm going to go ahead and do this. I'll let y be x over here and let x be y. And I'm going to go ahead and solve this for y. I'm turning the function around. And what I have here now is if I subtract that 6, I have this, and if I divide by 3, I'll have this, and I'm going to claim that this is now the inverse function to the original f of x function. Right? Okay, and watch, it literally is the reverse operations. Here I multiply by 3 and add a 6. Here I subtract a 6 and divide by 3. It's not only the inverse operations, it's also in inverse order. So what would happen is if I ran a number through the function and then ran it through the inverse function, I'd be right back to the same number, right? And by the way, this was a multiple choice question, so let's just go ahead and see if we find the inverse function up there. it looks like it's C. Oh no, that's the wrong notation. It would be this right here. So the inverse function is x minus 6 over 3. So the answer was D. But let's just go ahead and I'm going to just show you a practical proof and then a theoretical proof that this is the inverse to the original function. For example, let's say I just used the number 2. So in the original function, if I put a value of 2 in, well, let's see what I would get if I found f of x when x was 2. If I put 2 in there in the original function, I would get 3 times 2 is 6, and 6 plus 6 is 12, right? But if I went and looked at 12 as being the input, right? Remember that x and f of x versus x and f minus 1 of x, they are inverses. So imagine if I did this then instead. If I said, all right, let's see what happens if I used 12 as an input to this, right? Remember, the outputs to a function are the inputs to an inverse. So I bet I'm going to get 2 coming out of this if I went and used this function. Let's try it. Here I would get 12 minus 6 over 3, which is 6 over 3, and I get 2. And this inverse function is allowing me to get back to the original x value here, right? So the input here that produced 12, if I use 12 as an input to the inverse function, it should turn everything around and get me back to 2, and it did that. But not only that, I could use that idea to prove that this is the inverse function from a theoretical standpoint. And here's what I'm going to say. If these really are inverses of each other, it's kind of like walking out a door and then walking right back in. It's as if you never left, right? It turns things right back around to where you started. So if I started with x and I got this for an answer, and then I took that answer and put it in, I should get back to x again. So let's generalize this and not use 2, but we're going to go ahead and actually do a composite and put this into the original function and see if x would come back out. So the theoretical proof that you have found an inverse is this, that if you do the following composite work and you say this, you take the inverse function and you put it into the function, because this should go ahead, being done on the original function, should turn everything right back around and I should get x. It should also be true that if I put the original function into the inverse function, which is kind of what I did here, right? I put the answer to the original function into the inverse function and I got back x. It should happen theoretically as well. So I'm going to put the function into the inverse and I should get x also. And if both of those things happen, then this is an inverse. F minus 1 of x is an inverse of the original f function. So let's see how we do composites. This is why we covered composites in 6.1 before we ever got to inverses. And so if the original function is 3x plus 6, this is going to look like this. And this is a question at this point. I do believe it should turn out to be the case, but let's prove it first. So what we're going to do is we're going to say that I'm going to do the f function on f minus 1 of x. Well, the f function is to take 3 times an input and add 6. But our input is actually going to be the f minus 1 of x function. So I have this. Now, it also says that after you put that in for x, the f function says to add 6. So I have that right here. Let's see if that does eventually give me x. Well, right here, this would cancel, and I get x minus 6 plus 6. And, yeah, they must have been inverses of each other. But let's prove it in both directions. So over here, I'm starting with this inverse function, and my input is to put the f of x function in for x. And let's see if that produces x at the end. So what I have is, instead of x, I'm putting the f of x function in there, right? So I'll have 3x plus 6 going in for x. And then I'm going to go ahead and do the rest of the inverse function, minus 6 all over 3. And that turns out to be 3x over 3 because 6 and minus 6 cancel. And I do get x equal, right? I do get it equal to the other side, what we hoped would happen, right? This worked out both ways.